There we go. Okay, so chapter 14, multiple linear regression. So remember last week with simple linear regression, I just simplified it and I just use the initials SLR. I do the same thing here, MLR. So multiple linear regression. Like I already stated, this is the case when we have more than one predictor, which is my X variable. Okay, so that's the case with multiple linear regression. So we still have our Y variable, and Y is still numerical, okay? We're still looking at all numerical variables right now. I'm just gonna put a 1 here so we know we only have one of those. And X is numerical as well. We'll get into when it's not numerical later on, but not today. And we could have multiple. I'm just going to make a note that X can be categorical, but we're not going to do that today. So today we're just going to stick with all numerical, but we're going to introduce more than one X predictor that's numerical. Okay. So as you know, we'd like to get to know the data by looking at some graphs and maybe some values and just kind of get an idea of what's going on with our data before we actually test for any significance. So when we get to know our data, we could do a few things, and very similar to last week, where we can create a scatter plot, but we're going to actually call it the matrix plot. And the reason for that is because it's a matrix of scatter plots. So, oops, I did not mean to do that. So it's our scatter plot. I didn't really want to have that there. Okay, so our matrix plot, this is just multiple scatter plots. Each showing the response variable, which is my Y, versus each predictor, my X, and it's also going to show the predictor versus all other predictors. So my matrix plot is going to give me more than just the Y versus each X. It will also give me X against each X. So you're going to get a lot of information from this matrix plot. Remember, it's just a visual, right, about what's going on, but it gives us a really good idea if there's a relationship between X and Y. So what we do here is we're going to enter our X and our Y in a very specific order in Minitab. So we can look like just at the top row or something like that. So then it's a really quick scan visually about what's going on. Okay. Then, of course, with our scatter plot, like last week with our scatter plot, we also got our correlation value. And that correlation just kind of confirmed, right, what we were seeing. And it gave us a little bit more, like a stronger understanding of how that strength was between X and Y, right? Because we have our scale. So we're going to do the same thing here. But again, since we have multiple predictors, it's not going to be just one correlation value. We're going to get multiple. And so this will be our correlation matrix. So again, it's just going to be a matrix of all of these different values. So it's a table that gives the strength. Remember, correlation, R, gives us the strength of the linear relationship. So it's very important for us to make sure we write that linear relationship, not just any relationship. Between the response, obviously it's Monday, I'm having a tough time. Her response and each predictor. Okay. Again, ManyTab's going to do this all for us. We're going to enter our X and Y's in a specific order. I'm going to show you and go over it when we look at our example. And so we can just look at, you just have a really quick visual and really just read through these numbers quickly. So we're not all over the place in this whole table. Okay. Then of course we're going to interpret this. So when I ask you to interpret, your scatter plot and your correlation, I don't want you to interpret all of them, because if you have quite a few predictor variables and you've got a lot going on, we don't want to talk about them all. We just want to talk about the strongest relationship. So skim through the numbers and skim through your visual up here and look at which one's the strongest relationship and report about that one. I'm going to talk about that strongest linear relationship. We don't want to talk about all of them, but there may be more than one that's strong. So we'll make a note of that. So in that case, if I have maybe 5 predictors and 2 have very strong relationships, I'll just talk about both of them, right? And I'll just interpret and just, give a little statement about both of them. But we don't need to talk about all of them, okay? And here, of course, we use our correlation and we will use our graph. Okay, so we'll use those two to make that interpretation. So I just want to mention, we're not going to do a lot with this, and we're not going to do anything else with it today. But I want to mention that we may see a strong linear relationship between 2 predictors. And what we're interested in right now is we're interested if there's a strong relationship between a predictor and the response, right? That's all we're interested in here. So when I'm talking about the strongest linear relationship, I'm talking about between X and Y. And that's what we're going to report here. But I want you to know you may see a strong relationship between 2X. So 2 predictor variables. And that's called multicollinearity. Okay. And it's just saying that one predictor can be linearly predicted from the other predictor variable. So one X can be linear predicted from the other X. And that's all we're going to talk about it right now. You may see it. You don't have to mention anything in here about it. You could, but I'm just letting you know, we may see that. We don't have to really say anything about it right now. Okay. Because we will see those numbers, we'll see those graphs in here. All right, so let's talk about when we fit our model and what we're going to do with our model here. So of course, it's all about knowing if we should make predictions, right? If we should use our model to predict a Y given an X, right? That's always what it's about. So of course, this is still our regression analysis. So anytime you see regression analysis, it doesn't matter if it's when you have one predictor or two predictors, what we're talking about is building our model. So fit the model. We're going to do the same thing we did before, right? So I'm just going to write same as last week. So we will go to the same place in Minitab. And of course, I'll show you the example. We'll go to the same place in Minitab and we will build our model. We're going to put our response variable in and we'll put all of the predictor variables in. Our population equation is going to look a little different now. So remember I showed you the population equation last week for the simple linear regression when we had 1x. So now our population equation, when I have multiple x, it's going to start out pretty similar where we have our b naught plus, or beta naught, I'm sorry, beta 1, x1, right? And then I had epsilon. But this is because I have one predictor, x1, and now I have multiple predictors. So I have beta 2, x2, and this will continue all the way up to beta k, xk, plus my epsilon I. So the difference in this equation is that I'm going to have a term for each predictor variable here. So I'm just going to remind you that epsilon is my error term. That hasn't changed. That's still my residuals, okay? And now K represents the number of predictors in the model. So if I have 3x variables, 3 predictors, and I'd have beta 1, x1, beta 2, x2, beta 3, x3, then epsilon, right? So it goes up to k. K is just indicating how many predictors. If I have 2 of them, I only have 2 here. If I have 5, I'd go up to 5, right? So that's what our populations equation is going to look like. And then our sample equation or estimated equation. I'm going to write sample. This equation is going to look very similar. Y hat I, you know I'm going to use B here, not beta now. B naught plus B1 x1 plus B2 x2 plus all the way up to BK xk. So I want you to think about this. Normally when we have a simple linear regression, we have one slope, right? And that would be beta 1. We wouldn't have all this in between here, right? And we would have one slope of our line. It's different now. When we have multiple linear regression, you can see the terms are different. I have more terms, one for each predictor. I have what we kind of looks like multiple slopes, right? But we can't really refer to it in that way because I don't have just one, right? So I can't really refer to them as slopes. So we call these the coefficients of the predictor, which that's what a slope is, right? I mean, I know when we think about an algebra, the slope is how the line looks, right? The slope of the line, and that's exactly what it is. But if you think about it, it's just the number in front of x. So it's the coefficient in front of x. So here, what we're going to talk about with multiple linear regression is that our beta is our coefficient of our predictor, our x, okay? So we can interpret the coefficients of the predictors very similar way how we interpreted the slope for our single predictor last week. So we're interpret the coefficient of the predictor variables. So here, what we're going to do is we're going to say, we're going to interpret each one individually, but we're going to say holding all the others constant. So we're saying if all the other predictors are constant, meaning they don't change, then I can interpret this beta or this B, right? So that's what we're going to say. So it's just like a little statement at the beginning or at the end of my interpretation. So holding all other predictors constant for each unit increase in my predictor the response y variable will either increase or decrease by the absolute value of the coefficient and then we say on average. You know, if you don't put the on average, I'm not like a really big stickler for it, but really that's what it is. It's on average. So this is my increase or decrease. So of course it's increase if that coefficient is positive and it's a decrease if my coefficient is negative. And it's by the coefficient, okay? So all I'm really adding is this statement, right? Everything else is really the same. I'm just adding the statement, holding all predictors constant. You can add it anywhere as you want, right? So you can always use my statement. You don't need to use my statement. You can write your own statement. So you can say for each unit increase in X, the Y will increase by the coefficient, right? You're gonna fill it all in. Let me put that there. And then you could say after holding all other predictors constant or holding all other predictors constant, that kind of thing. Just adding that in there so we know it's not just the regular slope because we have other stuff going on. So we want to just make a note of that we know that there's other stuff going on. So that's looking at our regression analysis. That means looking at our equation, right? That's what we're interested in here, the equation. So you guys know when you're working through these now, you get a lot of output here. When we build our model, when we fit our model, we're looking at the regression analysis. You don't have to just put your equation here, but you can, right? You can put all your output if you want, and then you keep referring back to it. Some people like just to put the equation here, address this stuff, and then put the rest of their output in different places in their work. It's up to you. So sometimes I just put it all in one spot and then I refer back to it, and that's completely fine. So I just like to mention that. So I know sometimes I get questions on that stuff, like where do I want the output? Okay. All right, so that was our regression analysis, and with our regression analysis that's fitting our model. So now I want to look at our test for significant regression. So we did this last class last week here. It's going to look a little different today. So this is our test for significant regression. We're still looking at, is the model statistically useful? That's what we're still looking at. Is our model statistically useful? I want you to know there's another name for this, and I will try to write them both, but this could be also called the test for model utility. And all it is saying is the model statistically useful. So it could be significant regression or model utility. So sometimes I'll write, like on the daily, test for significant regressions, I put in parentheses, model utility. This is going to be a shortened test process. I'm going to write the simple linear regression over here, or maybe I'll write it over here, just so we can compare what we did before. So it's a shortened test process. What we did, I guess I'll write it over here. For our simple linear regression last class or last week, we defined beta, right? So we defined beta, we identified our null, and that our null was that beta was equal to 0. We identified our HA, which was beta was not equal to 0. Then we reported our T, test statistic, or degrees of freedom, and our p-value. Then we wrote a conclusion. Right? So these were the things, the few things we included in our write-up last week for simple linear regression. Now, this week for multiple linear regression, we're just going to cut it down a little bit and you're going to see some of these things change. So here for multiple linear regression, we're going to identify our null and our alternative. Our null and alternative are still the same, but we don't have one beta anymore, right? We have multiple betas, right? We have a beta for every predictor. So I can't just say beta is equal to 0. I have to list them all. So you could do it a couple different ways. To me, the quickest and easiest way is saying beta 1 equals beta 2 is equal to all the way up through beta k, and that they're all equal to each other, which they all equal 0, right? Because that's saying that the model is not useful when I have a slope of 0, right? A horizontal line. We're saying our model is not useful. So HA is that at least one beta does not equal 0. So I'm going to write it like that. So you know you can write this different ways, right? Because you're typing it up, it's not always the easiest to find beta. You can find it and insert it with your symbols. But if you don't want to do that, you could write out beta, right? You can use a capital B. Someone asked me that. That's fine for me. So you could say, at least one. Beta is not equal to 0. You could use symbols. You could write this out, equal 0, not equal 0, whatever you want to do, right? So remember, if it's not equal to 0, this means the model is useful. So if my HA is true, then that means the model is useful. So now here, I'm going to report our F test statistic. So think back to our analysis of variance, right? We have the F test statistic. It's the same thing where it's the MSR divided by the MSE, okay? So our F test statistic is the same calculation as before. It's still on my skewed right curve. It's always a positive number. It's a fraction, right? So I'm going to report this value. And then of course, I'm going to report the degrees of freedom that go with it. And remember, since I'm reporting an F, it's a fraction, I have 2 degrees of freedom. So my degrees of freedom here will be K. So remember what I said, what K was. K is the number of predictors in the model. So it's easy to identify, but it's given to you in your ANOVA as well. And the second predictor is what we talked about last week, which was n minus 1 minus k. That's from my error. So this is all going to look very similar to what we did with our ANOVAs, okay, several weeks ago. So k, this is going to be from my regression. We'll see it in the output. I'm going to show you the output in a minute here. from my regression row, and then from my error row, n minus 1 minus k. So it's my n minus 1. And remember last week I said, well, this is always going to be n minus 2 for simple linear regression because k was 1 because I only had one predictor. Now it depends on how many predictors. So if I have 3 predictors, then it'll be n minus 4, right? So it just really depends on how many predictors we have in our model. My degrees of freedom. Again, my ANOVA will give me this. Okay. Of course, we're going to report our p-value and then our conclusion. So it's a nice short test process. There's not a lot to write up here. The conclusion is the same conclusion as last class. So it's about if the model is useful. So I'm just going to write it right here. So if the p-value is less than or equal to my alpha, then the model is useful. You know, I like you to write a nice statement and conclusion with context. I like you don't even have to tell me the p-value is less than alpha, right? You can just write a nice conclusion at the 5% level of significance. You know, our model predicting y given these different x's is useful, that kind of thing. Okay, so nothing really new there with this. What's new is that we're dropping defining beta because there's too many of them now. So we're not going to do that. We're reporting F. It's a fraction, so I have 2 degrees of freedom. That's our biggest difference from last week with this. I want to take a look at the output so we know where we're looking. So when we're looking at the multiple linear regression test for model utility or the significant regression, we're going to study the ANOVA. So let me just write this here because I want you to know where you're looking. This is going to be in the ANOVA. So my analysis of variance, part of my output. We used it a little bit last week, but not a lot. I'm just going to switch my screen. I'm going to look at day 23, because that's what we're on. Day 23 typed notes, page 4. I just want you to see what this output looks like. So if we go to day 23, I'm not even on the right page. I'm down a little ways here. Sorry about this. So page 4 right here. So our analysis of variance. What I want you to know is it's going to look very similar to what we looked at before when we were just in numerical data, not in regression, and we were studying ANOVAs, right? So we had multiple populations. We studied that top line, and that's where we're going to be at again. There's going to be more than just 2 rows, right? It depends on how many predictors we have. But we're going to study this top line. That's going to give us our F test statistic, and it will give us our p-value. And then you can see right here, I highlighted in yellow, also our degrees of freedom. So it's going to be from our regression line, okay? And then our error line. So I just want you to know where you're going to get it. Of course, we're going to work through an output or work through an example, and we'll take a look at the output together. But I want you to know that's what we're doing. So now this test is very similar to our ANOVA test before, where it might tell us that our model is useful, but it doesn't tell us which predictor is useful. So it might tell us that we have a useful model and that we have a significant model, but it doesn't tell us which predictor is significant, meaning which predictor actually has that strong linear relationship. So then we need to take it a step further. So of course, right, this seems to happen often when we have this kind of thing. So we need to kind of perform like a follow-up test when we have a useful model. I'm going to write it here. Plus our follow-up when the model is useful. So if the model is useful, we want to know which predictor is useful. So I'm just going to say when we reject the null. So when we reject our null, we're going to move on and do a test for individual predictor significance. Okay, so I'm going to write that on the next page. So that's our follow-up. So our test for individual predictor significance. So I want you to think back when we were looking at the ANOVAs and we did this, right? When we had multiple predictors in our ANOVA. And if it was significant, then we went back and looked at which ones. It's the same idea behind it, right? So we're going to do this. So we're going to actually here, I just want to write this down just so it's, a continuation. So we're only going to do this only if we reject the null in the test for significant regression. Okay. Only if the model is useful. Okay, just so we're clear on when we're doing this. So here we're going to study the coefficient portion of the regression output and look at each predictor t-value and corresponding p-values. Of course, if a p-value is less than alpha 0.05, we're going to use all the time, then that predictor is significant. Sorry about all this writing, but I like to have it in writing. So we're going to study the coefficients portion. So this should be already familiar. We've done this before with looking at this coefficient section last week. So we're going to study that. We're going to look at each predictor individually. We're going to look at the t-value and the corresponding p-value. If the p-value is less than our alpha, then that predictor is significant. We're not going to do a full test write-up on this. We're just going to write a conclusion. So for our conclusion here, you're going to write it for each predictor that is significant, okay? So a conclusion only for the significant predictors. So if my predictor is significant, then I'll write the conclusion. So we'll say something like with a t-value equal to whatever it is, and a p-value equal to whatever that is, the predictor variable is a significant predictor. Now you can write it in a different way. You could say something and you could give more detail, something like the predictor variable is a significant predictor for our model that predicts y given that x, that kind of thing. So we're going to write our t-value there and our p-value there. I don't think I have to fill anything there. And then this is just going to be our predictor. So whatever it is in words, right? Don't just write x. Don't write x1, write what it is. If it's height, write height in there. Okay. And we're only doing this for are predictor variables that are significant. Well, how do I know if it's significant? It's significant if my p-value is less than alpha. So you're going to quickly look through them, pick out the ones that are less than, that means they're significant. Okay, so that means that they are, that is a predictor variable that actually has a nice linear relationship with my y. Okay, so that's what we're going to do today. So we're going to test for significant regression up here. If this works out, then I want to take it a step further and test for each individual predictor significance and see which one is significant. It could be more than one, right? So you could have 5 predictors. You could show that the model's useful, but now you want to know, well, what part of it's useful? You're going to look at the coefficients and we'll state maybe you have 2 that are useful, then we'll use those 2 and just make a separate statement for each one. So maybe I'll write that down. So conclusion for each. Significant predictor. Okay, so you're not going to just make one conclusion, you'll make multiple conclusions if you have multiple predictors that are significant. So this is for significance, right? If something, one of our predictors is significant. Now remember last week we started talking about, we talked about if the model was good for predicting. So this is statistically good, right? And now we want to talk about practically useful. It's really, this is not as strong as the statistically usefulness, right? So this is what we did when we studied R squared. So we want to know, is the model good for predicting? And we call this practically useful. This is like the easy way out, and this is studying our R squared. Okay. So here we're going to study the R squared adjusted value. So remember we talked about this. So some of you asked, we had an R squared, we had an R squared adjusted right to the right of R squared. Today we're going to use the R squared adjusted. So we use R squared adjusted for multiple linear regression. Okay. We're going to use for multiple linear regression. And the reason why we use the adjusted for multiple linear regression is because the R squared value is adjusted to provide that proportion of variability in Y that's being explained by the model for all of the different predictors. Okay, so it's been adjusted for having multiple predictors. So you know, it's as we looked at last class, and maybe you didn't really look at the adjusted, and it's okay, but it's, if you look at it, it's not too far off from the regular R squared. It's just adjusted slightly for having multiple predictors in the model. So it depends on how many numbers or predictors are in the model, it's going to adjust it that much. Okay. So we're still going to use what we did before. So we're still going to use the R squared, but now it's R squared adjusted is greater than or equal to 75%. Okay, we're still looking at that. So we're still going to use it 75% to see that that's high enough to say it's good for predicting. This is like our quick way of seeing if the model is useful, right? It's not our statistical way. So we might be asked if it's practically useful, and this is what we're using R squared. Remember, we use this loosely. It's a rule of thumb. So if it's like 73%, then I would probably still say, yeah, it's close enough to 75%. It probably is good for predicting. But if it's something down lower, like maybe 60%, maybe I would say, you know what, it's not close enough to 75. I don't think it would be good for predicting, that kind of thing. Okay. Any questions before we look at an example today? So I want to take a look at example 1 on page 11 today, and we'll work through all this. We're also going to take a look at our requirements. So our residual analysis, which is really the same thing as last class. There's nothing new. Okay, so I don't have any new notes on that. Okay, so in example 1, I'm going to pull this up and I have my mini tab. So feel free to go into the day 23 notes if you want to work along with me, or you can just watch and follow along that way. So here, let me just see. Okay. All right. So here we have our, let me see, my example, page 11. Let me go down. I was already on this originally. And then I had to move. Okay. So example 1 on page 11, we're talking about people who work in forestry, and they need to be able to estimate the amount of timber in a given area, right, of a forest, so they could do their job properly. So we have some data, and it's a sample of black cherry trees in Pennsylvania. And we have our data, it's already in mini tab, so I don't have it shown here, but I tell you how many predictor variables we have and our response. Our response variable is going to be the volume of trees. And I want to know if the diameter can predict the volume, or maybe if the height could predict the volume. So I have 2 predictors, diameter and height. Okay. So the very first part of the problem, I'm going to go through what we need, and then we'll go into mini tab and we'll get it all at once. So the first part wants us to get a scatter plot. So that's where we're going to get our matrix plots. Then the second part has our correlation matrix. So that's the table of all our correlation values. I'm going to show you how to get that and how to put everything in the same way every time, so it's quick when you read it. Then part C is just saying, make a statement about your strong linear relationships. Okay, so that's really nothing new for us, other than we're going to look at a matrix, a table of these plots and of these values. Then part 2, it says perform regression analysis. This is just building my model. I remind you here, build the model, right? We want to fit the model. I tell you what my predictors, it says predict the volume given the diameter and the height. Then in 2B, it says interpret the coefficients of the predictor variables. So that's where it's the slope interpretation. It's the same one that we've used before. Now we're just going to make sure we mention that we're holding the other predictors constant. Then in part 3, we want to test for significance in our regression for our multiple linear regression. So it's called model utility for the multiple linear regression. So we're going to run that test for significant regression. If it's significant, then we can test for the individual predictor variable or predictor significance, okay, down here in part B. Then in part C, it says build a CI about beta for height, and then in D, beta for diameter. So all I'm saying is I want to build a CI for beta for my height, and then for my diameter separately. So I'm going to show you how to do that. It's going to be the same thing as last class. And then part 4, is the model practically useful? That's my R-squared adjusted, and then my residual analysis. So let's go on over to mini tab and just take a look at what we need here. So I already have my mini tab data. So it's tree data under day 23 in the notes. So remember what I did last week where I said I can rename some of these? You might want to do that. Like you could call this X1 if you wanted for diameter. You don't have to. You could call this X2 or predictor 1, predictor 2, oops. Or you could just write X and X, predictor and predictor. But I think what's really the most helpful is renaming volume as our Y. Because, oh my gosh, I keep going too far. Okay. Because I think that's the one that needs to stand out to us. We're always putting it in the correct location for our response. Okay. So I just renamed those. It's nothing you have to do. It's just something you can do. I like to mention like little tips and tricks that might make things easier for you guys. So in the very first part, we want to get to know our data. So it's building our matrix plot and our correlation matrix. So we'll start with a matrix plot. You know, there's multiple ways to get these things after doing the simple linear regression last week, and it's going to be the same. So we can go to graph, and the second option down says matrix plot. So we can take a look at this to get all the different scatter plots. So I'm going to click on that. We're going to just choose simple. We don't have anything with groups or anything yet, so we don't need to do anything with that. So I'm just going to choose simple right off the bat and then click OK. So it just has one box for my graph variables. So what I want to do here is I want to select my Y first. I know this is different from what we did before, but you have to remember we don't have one scatter plot. We're going to have multiple scatter plots. So I'm going to choose the Y and double click on that one first, and then I'll bring the other ones in. It does not matter the order on the X's. It's not going to change any calculation you have going on. It's just changing the order of how you're going to view it in your matrix. So then one other thing I do here is I go to matrix options, and I just ask for my display to be upper right. Now, the upper right goes along with me entering my Y in first. Okay. I'm going to click OK from here. So we get a matrix, but I only got the upper right. I didn't get the full matrix because it's going to be the same plots, just reversed on the lower end. I don't need to look at them twice, right? I just need to look at each one once. So you will see when I put my Y in first, it put the Y on this first row. And what that does for me is for my my scatter plots for Y versus X, it doesn't matter how many X's I have, I will always just look right along the top at that top row. And it's really nice to look at that. Okay. So here we can see I have a nice linear relationship between the volume and the diameter. Do you see how that is read there? And then over here, I could just move it up like that. Then this one over here is volume with height. So height doesn't seem to be as strong of a predictor. On a Mac, there aren't any options to select the upper right or anything. Okay, then don't worry about it. You know, I know there's some slight differences when we see the Mac version. When you're on your Mac, do you at least see these three on the top right? I guess that would be my next question. Because what I want it to be is I want it to be easy for you guys when you look at these. I'm going to show you another way to get these scatter plots, but I want it to be easy for you. So if you always put the Y in first and the X's in second, that you can just look at this top row and have a quick visual that way. So I'm kind of hoping for that. Yeah, you're going to get 6 rather than 3, but I want to know, is your Y, but yes, you have the 3 plots, and are they in the same order as mine? Meaning maybe not the X's, but is Y the top row? I guess that would be like, does your top row look like my top row? But maybe they could be backwards order because I didn't have a specific order for my X's. I guess that's what I'm wondering. And we can always look at this. I can have someone share their screen. Yeah, they're in the same. Okay. So that's good. It's okay if you can't get a top right. It just means like Lindsay was saying, you're going to get 6 plots. So you're going to get another one here and then 2 more down here. And it's okay. It's just, you could just ignore those bottom ones. And what we're really looking at is this top row. So that's the importance of putting Y in first. Okay. Thank you so much for sharing that. Let's take a look at the correlation matrix. You're going to see when we do the correlation matrix, we're going to get the scatter plots there as well. So if we go to stat, remember correlation's under basic. It's like the only piece that's under basic. Everything else is under regression. You go right to correlation like we did before. So we take a look at the correlation. Now here, we're going to actually enter them in reverse order. So we're going to select the X's first and then the Y's second. And the only thing for this is because I want you to be able to read the bottom row. So I'm not trying to like have a hassle of like remembering which one's which. But you can bring in your X's first and your Y's second on the correlation. Okay. I'm just going to click OK. I'm not going to do anything fancy here. So if you click OK, I want you to take a look. You have your scatter plots right here as well. So if you just want to get them from here, it's completely fine. I'd like to show you different ways to get the same thing. And this is just one of those days. So right here, we can see the Y is on the bottom. Okay, and that's what we're really interested in. So Y with diameter and then Y with height. Okay, right here, the bottom two. Just keep scrolling down to actually get your R values. I know you can see your R values here, but I want to show you the table of just the R values, and that's here. And this is really why I put the Y in last, is because it gives me my Y on the bottom row, and right here it is. So here's my Y, the 0.967, and then the 0.598. So seeing the correlation value, my R value, and with the graphs, I can see that diameter seems to have a pretty strong linear relationship, and it's a positive one, right? With volume. So as diameter increases, my volume is also increasing. The height also has a linear relationship. It's just moderate though, right? It's 0.598. It's just moderate. And then I just want to show you here, this 0.519, this is height with diameter. It's the two X's together. Okay. We're not really studying that right now. Okay. So I just like to, show that to you guys. All right. I just have to assign the captionist. So let me do this. Okay. All right, so I'll go back to my screen sharing and we'll go back into Minitab so we can see. Okay, so that's just getting to know my data. We just make a note about that strongest relationship. So I would only talk about the diameter versus volume on this one because that seems to be the strong relationship, and there's only one that's real strong. The other one's moderate. Okay. Any questions on that first part of this example where you're just getting to know your data kind of thing? So you can use the scatter plots from this output for that scatter plot. You don't have to go into the graph section if you don't want to. Okay. All right, so in question 2, it says to build the model. We're going to build the model the same way we did before. So we'll go to stat, regression again, and fit my regression model. Same place as before. We don't have to do anything different. So when we go in here, it's going to ask for my response variable. Remember, this is my Y. Let me bring that in there. My predictors, I'm going to add both predictors. The order does not matter. So I'm going to bring both predictors in. Does not matter which order you bring them in. And you only use those first 2 boxes. Remember, we're not using that third box. Not yet anyways, okay? All right. When we're going to perform residual analysis, I probably should do a couple of things before I get out of the screen, right? Also, if I need a CI about a beta, I probably should ask for that now. I don't have to, right? I could easily go back into this model and get it then, but I like to get everything at once if I can. So I'm going to do that. The same thing as before. It's the last 3, okay? Graphs, results, storage. So the same as last week. I'm going to go into graphs. I want to get my residuals versus fits plot. This is for my residual analysis. And of course, I want standardized, remember, so I can look for outliers easily. Just click OK. Results. This is where I want to get my expanded tables, just like last week. Expanded tables. I do this so I can get my CIs in case I need them. And I did read a question that asked for them, 2 different spots, okay? So I do need that. Remember, if I need something other than a 95% CI, which we don't really do here, you can go into options and change that level. We don't really need to do that, but I like to give it to you and show you just in case. Right here's my CI level under options. That's only if I need to change it from 95. So you probably won't need to do that for me, but I don't know about the homework. Normally not, but I like to show you just in case. And then storage is the last part. That's so I can get an NPP, right? So I'm going to ask for either the residuals or standardized residuals. I typically just stick with standardized because I did the standardized for my plot. You don't have to, you're gonna get the same results either way. So whichever one you feel like choosing. I'm gonna click OK and then OK again. So the first and the last one, that's just for my residual analysis, and that was the very last part. So here's my output. So remember when we're going to build the model or fit the model, my regression analysis, I'm really looking at my equation, right? Getting my equation. But at this point, I would probably just take all of my output. There's a lot here, and I would probably put it all into my paper at this point because I'm going to use a lot of this, okay? So in 2B, it asks me to interpret my slopes, basically, okay? We don't really word it as that because it's not really the slope of the line anymore because I have multiples. So it's not really called the slope anymore. So I'm going to interpret my coefficient for my predictor. So I want to interpret this 4.7 in front of diameter and the 0.339 in front of height. So remember, you can get these numbers from the coefficients box, right? They're right here. Diameter 4.7, height 0.339, okay? So I want you to know you have them here. Remember, if you need to expand your decimal places for your homework assignment, you will right click on this box and after they're highlighted. So all I did was I just clicked on them to highlight them, right click, decimal places, and you can expand it as far as you want. And there it is. You might need to do that for your homework, okay? Same with the CIs, you could do that, right? I just want you to know this is where you can do it. You can't do it like up here in the equation, okay? You can do it here in this coefficients box. So my interpretation would be something like holding the height, I could be specific, holding the height predictor constant for each inch increase in diameter, my volume is going to increase by 4.7, okay? And then I could do the same thing for the height. So holding my diameter constant, each inch increase in height, the volume will increase by 0.339, right? So it's very quick and simple interpretation. It's the same thing we've done before in the past, okay? So nothing new. Part 3 says test for significance regression. This is my model utility. The reason why I know it's model utility, it's multiple linear regression. It's the same thing as before. So my null is that all of the betas are equal to 0, meaning beta 1 equals beta 2 equals 0. I only have 2 because I have 2 predictors. My HA is that at least one of those betas is not equal to 0. Okay. So now for my model utility, I'm going down to my analysis of variance. So this part of my output to get my information. I'm going to report my F test statistic. It's in my top line. It's my regression line, 254. That is huge, right? If it's that huge, you know your p-value is very small. You know you're going to reject your null. You know your model is useful at this point, right? Just looking at this. If you need to report your degrees of freedom like we usually do, it's 2, which remember it's K. So we should already kind of know it's 2 because that's the number of predictors I have, and my error, 28. Okay. So it's the number in my sample, which is 31. It said it before in the problem, minus 1 minus K, which is 2. Okay, so that's where the 28 comes from. All right, my p-value right here, very small. So my conclusion is that this model is useful. Okay, so the model that predicts volume given diameter and height is statistically useful. That's my conclusion. Okay. Then, since I am rejecting my null, I want to go ahead and test to see which one is useful, which one's significant. It could be both, or it could be just one. I know at least one because my whole model is useful, right? So this is where I'm going to go up to my constants output, my coefficients output. I'm going to study the row for each predictor individually. I'm not going to do a test right up, but I'm going to look at diameter, right? Under diameter, I'm going to report my t value and my p value in my conclusion. So I'm going to say with a t value of 17.82 and a p value of very small, the predictor diameter is significant in this model. You could say in the model that's predicting volume. I'm going to do the same thing for height. Remember, you only write the statement if it's significant, if it's useful. And it is because you can just look at your p-values. They're both less than 0.05, right? So they're both significant. So again, I would say the same thing. With a t-value of 2.61 and a p-value of 0.014, height is a significant predictor in my model that predicts volume, okay? So you just make two separate statements and that's it for those. Only make the statement if your p-value is less than alpha 0.05. You don't need to do it if it's not, okay? Now, the next part says we want to identify the CI for height, right? So I asked for my expanded tables, which is right here. So for height, it's right here. So remember, we're describing the coefficient of that height predictor. So I'm saying that in the population, that coefficient of beta of that predictor height is between 0.07 and 0.605, right? It does not include 0. That means it's useful, it means it's significant, right? Same thing as last week. Same thing for height, or for diameter, I'm sorry. So my CI for that coefficient in front of diameter, it goes from 4.16 to 5.24, not rounding properly, I'm like truncating. So that's the coefficient for my populations between those numbers. It does not include 0. It is also useful or significant, right? Now the last part wants to know, is our model practically useful? We're talking about R squared here. We're looking for it to be greater than 75%. But we don't just use R squared. We're going to use R squared adjusted because we want to adjust for having multiple predictors, and that's what this does. You would see they're very similar. So 94.42%, I would say that's definitely greater than 75%. So yes, this model is useful. So it is a good model for predicting Y values. And that's what that's about. Okay, let's quickly just skim through the residual analysis. You know, this isn't really a long process. Here's my standardized residuals versus fit. So the first one is we want to make sure there's no pattern. This is a tricky one. There could be a U-shaped pattern. It could be a parabola. Look at that. It looks like it could be a possible pattern. I'm not sure. I may make a note of that. I may say there looks like there could be a curved pattern. You don't have to be specific and name the curve. You could just say it looks like there could be a curved pattern. So I don't think that they're independent actually, okay? But I'm going to continue with my analysis anyways. Then the second part is, remember, I don't want to see a sideways V, meaning I don't want them to be all close, all the dots close to 0 here and then further away here. They're not because of these. If these weren't here, I would say, yeah, maybe I would, right? Be close here, then further away up here. But I have these far away up here on this upper left. So it makes me think that it's I probably don't see a sideways V. So I can say that there is constant variability or constant spread to my residuals versus fit plot. Then the last one is for this part of it, that we don't want to see anything beyond 3. I don't see anything beyond 3. This goes up to 3 if there's no dots quite up that far. And then this one doesn't go down to -3. So we're good with outliers. There's no outliers. Then the next part is building an NPP based on column 4 here. So remember, graph probability plot, just single, choose my standardized residuals and click OK. Remember, I'm looking for a p-value greater than 0.05, which it is, 0.6. So we can say that they follow a normal model, that the standardized residuals follow a normal model. So we're good with that. So I would make an overall conclusion saying that maybe this linear model is not valid. Maybe it's not the greatest model because it appears that there might be, a slight resemblance of dependency, meaning they're not quite independent. It looks like a pattern going on for our first check. Okay, and that's what I would state. Any questions on that one? That was kind of like a lot, and it was pretty quick because there was a lot of stuff that we've done before. Any questions on that for me?